Alright, gang, here we go. This is for Physics Unit 9, Part 4, Part 3. Part 4, Dot 3. Anyway, we're talking about power. So, previous two videos, we talked about current and resistance, and now we're going to talk about power. We're going to bring it all together, alright, and just kind of wrap up a little bit, give us the last stepping stones we need before we can really start drawing electric or wiring diagrams and so on and so forth. So, and circuits. Anyway, so electrical power. Power is the rate of energy consumption. All right, so how fast are you using the energy that's being supplied to you? And so because it's rate, it's always divided by time. Okay, so it's the change in the potential energy over time. And we've talked about power before. Okay, specifically though, we're talking about electrical power because that's kind of what we're focusing on in this unit. And this is equivalent to the equation shown below. All right, so the potential is equal to the current times the change in voltage. Okay, that potential difference. The SI unit for power is always joules per second or watts. Okay, and the current is measured in coulombs per second, and the potential difference is in joules per coulomb. You multiply these two guys together, the coulombs cancel, and you end up with joules per second. There should be a lowercase s. All right. Anyway, and so here's our formula. Electric power is equal to current times the potential difference. And we could take this idea here and plug it in to find the other two. So equations for power. So we know this is Ohm's law. The change in potential difference is equal to the current times the resistance. So that means if we replace our V with this guy, the power would also be equal to I squared times R. Okay. All right. We replace that V with that guy there, and then the last one here, so we'd replace our I here. So if we rearrange this formula for I, this would become I is equal to V over R. Okay, delta V over R. Anyway, so I equals, so we could replace this guy here and plug in our value here. So our power would be equal to the change in voltage squared over the resistance, right? The potential difference squared over the resistance. So these three guys here, 1, 2, and 3. These are our three formulas we have to find our power. All right, let's try a practice problem here. It says a toaster is connected across a 120 volt kitchen outlet. The power rating in the toaster is 925 watts. All right, what current flows through the toaster? All right, so we need to know current. All right, so we just learned that power is equal to, one of our formulas was power is equal to I delta V. So to get our current, we would just rearrange this guy here. So our I is equal to P over delta V. All right, and so I is equal to our power, which is 925 watts, divided by our voltage, which is 120 volts. And so we get, where'd my calculator go? Oh, there it is. So we get 925 divided by 120. We get 7.7. And the current units is amps. All right. So that's that one. It says, what is the resistance of the toaster? Well, we know resistance. We've got a handful of equations now to find resistance, but we could use Ohm's law, V equals IR. So if we rearrange this to solve for resistance, resistance is going to be equal to V over I. All right, so we could plug in our resistance would be equal to V over I, so that'd be our 120 divided by the current we just found, so that'd be 7.7. This would be volts, this would be amps. So we say 120 divided by 7.7, we get 15.58. All right, so it would be 16. And it would be ohms because it's resistance. And it says how much energy is consumed in 75 seconds. Well, energy is in joules, so really we need to solve for joules, and we know watts is equal to joules per second. So this is equal to 925 joules per second. So if we can just cancel out the seconds, we're good to go. So we'll multiply this by our 75 seconds. Our seconds will cancel, and we'll just be left with joules. So we say 925 times 75. We get 69,375. All right, 3 sig figs for this guy. So we get 6.93 times 10 or 69,300, or 6.93 times 10 to the fourth. And it'd be joules. All right, not too bad. And look, we got all the right answers. Good for us. Good for us. All right. Household energy consumption. So this is essentially this is more practical applications, what you're going to be dealing with pretty much for the rest of your lives. All right. Yay! Power companies charge for our energy. So they don't charge for the power that they supply. They charge by the energy. So really, they care about, well, how much energy did you use, not how much power was supplied to you. All right. And so they, instead of measuring it in joules, because joules are ridiculously small for what we're doing here, or for, like, powering computers and lights and ovens and refrigerators and air conditioners and so on and so forth. They measure it in kilowatt hours. All right, kilowatt hours. So it's kilowatts times hours, and a kilowatt hour is defined as the equivalent amount of energy use for if you ran 1 kilowatt of power, 1,000 watts of power for 1 hour. All right, so 1 kilowatt hour is the same as 10 light bulbs of 100 watts each run for 1 hour total. So that's a fair amount of energy. All right, or 1 light bulb of 100 watts on for 10 hours straight. All right, so you can see how, like, these light bulbs use quite a bit of energy, and so that's why using these more energy efficient light bulbs is one of the big ways we're cutting our energy footprint, cutting our cost here. All right, this is your good conversion for converting kilowatt hours joules. Okay, you can do it the long way by going back to watts and all this stuff, but this is the easy way. Just remember this: 3.6 times 10 to the 6 joules is equal to 1 kilowatt hour. All right, last little bit here, and we kind of talked about this very briefly in the last video. Transfer of energy from power plants to your neighborhood has to be done at high voltage and low current. All right, and so these are the two things that has to transfer energy. And the reason this is because the power lost in electrical lines is actually pretty big, because it's so dang long, right? It's a long ways from one place to the next, and so they're trying to minimize the energy loss. The power is going to be lost, but they want to minimize that energy lost. All right, and we know power. This is one of the ones we derived a couple of slides ago. Power is equal to I squared times R. All right. Now these power lines are good conductors, but they're very long. So this resistance is really low, but because they're so long, that resistance is still pretty high. Remember, one of the ways we can increase resistance is by increasing that length. All right. So anyway, so because they're so long, their resistance is actually still pretty high, and so because they're just going to be as long as they are, they can't really control that resistance. So in order to control the current, they're going to transfer it at high voltages. So by transferring it at a really high voltage, they can actually control that current, and therefore have a minimal power loss. All right. So it's kind of an interesting thing. Like, I'm not an expert on any of this stuff. Learning more as I go, but it's a really fascinating kind of big deal. All right, as far as being able to convert, send energy to people's homes so that they can power their lives, keep themselves warm, feed their families, have hot water for showers, and, so on and so forth. Anyway, so be able to work with Ohm's law and be able to derive all those different power formulas, be able to describe what it's measuring, kilowatt hours, and convert to those things is essentially what you're required to do. Anyway, so do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.